Every GPS calculation, every synchronized communication, and every precision timing measurement proves that Einstein's insights about the nature of space and time remain as relevant today as they were over a century ago. The smartphone in your pocket represents one of the most sophisticated applications of Einstein's relativity theories ever created. Each time you check your location or navigate to a destination, your phone performs relativistic calculations that would have seemed like science fiction to Einstein's contemporaries. These corrections operate invisibly in the background, but they represent just one application of time dilation effects that scientists can observe and measure. The most dramatic demonstrations of Einstein's predictions occur in environments where particles approach the ultimate speed limit of the universe itself. Particle accelerators, time dilation at light speed. The Large Hadron Collider at CERN accelerates protons to velocities so close to light speed that Einstein's time dilation effects become dramatically visible in every experiment. This massive machine, stretching 27 kilometers beneath the Swiss-French border, pushes charged particles to 99.99991% of light speed before smashing them together in high-energy collisions. At these extreme velocities, particles experience time at radically different rates compared to the scientists observing them from the laboratory reference frame. The LHC's ability to generate collisions at energies of 13 teraelectronvolts creates conditions where Einstein's predictions about time become essential for understanding what happens inside the detector chambers. Unstable particles that would normally decay in microseconds survive dramatically longer when accelerated to near light speed, allowing physicists to study fundamental building blocks of matter that would otherwise vanish before instruments could detect them. The top quark represents a perfect example of this phenomenon. Under normal conditions, top quarks decay so quickly that they exist for only about 5 times 10 to the power of negative 25 seconds, making them nearly impossible to observe directly. When created in high-energy collisions at the LHC, these same particles experience such extreme time dilation that their lifetimes extend enough for sophisticated detectors to measure their properties and decay patterns. Scientists have turned this time dilation effect into a powerful research tool, using extended particle lifetimes to probe the deepest secrets of matter and energy. The CMS collaboration at CERN conducted extensive experiments during the LHC's Run-2 period from 2015 to 2018, analyzing millions of collisions to search for any deviations from Einstein's predictions. These experiments tested whether top quarks behave consistently with special relativity regardless of the orientation of the detector or the time of day when collisions occurred. The results confirmed Einstein's theories with extraordinary precision, showing no evidence of Lorentz symmetry breaking even under the most extreme conditions achievable in terrestrial laboratories. The precision measurements from these particle accelerator experiments provide some of the most stringent tests of Einstein's theories ever conducted. Modern detector systems at the LHC can track individual particles through their entire life cycles, measuring positions accurate to micrometers and timing intervals accurate to picoseconds. This precision allows scientists to observe time dilation effects directly by comparing the expected decay rates of particles at rest with the observed decay rates of particles traveling at relativistic speeds. The measurements consistently match Einstein's predictions to extraordinary accuracy levels. Muon experiments demonstrate time dilation effects occurring naturally in Earth's atmosphere every single day through cosmic ray interactions. Cosmic rays striking the upper atmosphere create showers of particles including muons, which are unstable particles similar to heavy electrons. These muons have a mean lifetime of approximately 2.2 microseconds when at rest, which should allow them to travel only about 660 meters before decaying. Since muons are created at altitudes of 10 to 15 kilometers above Earth's surface, they should never reach ground level based on their short lifetimes and the distance they need to travel. The reality contradicts this simple calculation because muons created in cosmic ray interactions travel at velocities approaching light speed. Time dilation extends their effective lifetimes as measured from Earth's reference frame, allowing them to survive the journey from the upper atmosphere to the surface. Ground-based detectors routinely observe these cosmic ray muons, providing continuous natural demonstrations of Einstein's time dilation predictions. The Frisch-Smith experiment in 1962 measured this effect precisely by comparing muon decay rates at different altitudes, confirming the time dilation factor predicted by special relativity. These cosmic ray muon observations represent one of the most accessible proofs of Einstein's theories available to modern scientists. Unlike the complex experimental setups required at particle accelerators, cosmic ray interactions occur naturally and continuously throughout Earth's atmosphere. Simple detector arrays can measure the flux of muons reaching the surface and compare these measurements with the expected rates based on muon production in the upper atmosphere. The dramatic difference between predicted and observed muon numbers provides direct evidence that time passes differently for particles traveling at high velocities. Advanced detector technologies developed for particle accelerators have revolutionized the precision with which scientists can measure time dilation effects. Silicon pixel detectors can track particle trajectories with spatial resolution measured in micrometers, while sophisticated timing systems measure particle arrival times with precision better than picoseconds. These capabilities allow researchers to observe time dilation effects for individual particles rather than statistical averages, providing unprecedented detail about how Einstein's predictions apply to specific quantum events. The Null 63 experiment at CERN studies radiation processes in strong electromagnetic fields by directing electron beams onto crystalline targets. These experiments investigate how electromagnetic fields affect the timing of photon emission, revealing that this process takes measurable time and can be experimentally influenced. The results provide insights into how time operates at the quantum level, where particle interactions occur on timescales that approach the fundamental limits of causality. Particle accelerators have essentially become time machines that allow scientists to observe the universe's fundamental building blocks under conditions that existed only in the first moments after the Big Bang. The extreme energies and velocities achieved in these machines recreate environments where time dilation effects become dominant factors in particle physics. By studying how particles behave under these conditions, researchers gain insights into the fundamental nature of space and time that cannot be obtained through any other experimental approach. Every cosmic ray interaction in Earth's atmosphere provides natural validation of Einstein's century-old insights about the relationship between motion and time. The muons reaching the surface, the particle tracks recorded in accelerator detectors, and the extended lifetimes of unstable particles all demonstrate that time dilation operates exactly as Einstein predicted. These experiments prove that the patent clerks thought about frozen clock hands has become the foundation for humanity's most sophisticated investigations into the fundamental nature of reality. Yet even these extreme conditions may represent only the beginning of our understanding of how time truly operates at the deepest levels of existence. The future of time. Modern research continues pushing the boundaries of Einstein's theories towards scales and precision levels that reveal new mysteries about the fundamental nature of time itself. Quantum gravity research in 2025 explores how Einstein's theories might require modification at the smallest possible scales where quantum effects become dominant. Scientists work toward reconciling general relativity with quantum mechanics, seeking a unified theory that explains how space-time behaves when quantum gravitational effects become significant at the Planck scale. This represents one of the most challenging frontiers in modern physics, where our understanding of time itself might need fundamental revision. Advanced atomic clocks are achieving time measurement precision that would have seemed impossible just decades ago. The Atomic Clock Ensemble and Space mission, launched by the European Space Agency in 2025, represents the pinnacle of timing technology. According to Luigi Cacciapuoti, an ESA physicist who helped build and launch the device, this technology achieves such precision that it will not lose or gain a second in 300 million years. The ACES system combines two complementary atomic clocks, one containing cesium atoms and another containing hydrogen, working together to produce timing signals with higher precision than either clock could achieve independently. These space-based atomic clocks operate aboard the International Space Station at approximately 400 kilometers altitude, creating ideal conditions for testing Einstein's predictions about gravitational time dilation. The mission compares its onboard clocks with highly accurate ground-based atomic clocks worldwide, searching for tiny deviations that could reveal new physics or provide insights into dark matter models. The expected improvements in measurement accuracy would enhance current gravitational redshift measurements by a factor of 10, opening new possibilities for testing fundamental physics in ways that ground-based experiments cannot match. The ACES mission enables worldwide clock comparisons with precision reaching 1 part in 10 to the power of 17, approximately 100 times better than current GPS-based synchronization methods. This extraordinary accuracy allows scientists to detect geopotential height differences on Earth's surface with 10-centimeter precision, revolutionizing both fundamental physics research and practical applications like improved GPS navigation and telecommunication systems. The mission demonstrates transmission of ultra-stable time signals to Earth with uncertainties as low as 100 picoseconds, enabling global synchronization networks that far exceed current capabilities. Emerging technologies increasingly exploit relativistic effects for applications that extend far beyond traditional physics research. Professor Paul Couillard's team at the University of Illinois developed quantum interferometry tools using extreme color entanglement to enable faster and more precise measurements than classical or existing quantum techniques can achieve. These innovations find ready applications in medical diagnostics, remote system monitoring, and material characterization, demonstrating how Einstein's insights continue spawning practical technologies in unexpected fields. The ACE's mission may contribute to redefining the fundamental unit of time itself as optical clocks emerge as the future standard for timekeeping. Current satellite technology cannot handle the precision levels that modern atomic clocks achieve, creating opportunities for entirely new approaches to global time synchronization and fundamental physics research. The mission offers opportunities to probe whether fundamental physics constants remain truly constant over time by comparing ground-based clocks that operate using different atomic transitions. Scientists can monitor whether the fine structure constant that governs electromagnetic interaction strength varies over time. Any detected variation, however small, could indicate new physics involving dark matter, extensions to the Standard Model, or previously unknown aspects of space-time structure. The ACE's mission serves as a laboratory for exploring fundamental workings of the universe through precise time measurements, simultaneously testing both general relativity through gravitational time dilation measurements and special relativity through observations of time passage for objects in relative motion. Modern experiments reveal that gravitational effects influence time in ways that create practical applications Einstein never anticipated. The ACE's mission's ability to detect 10-centimeter height differences through gravitational time dilation measurements enables relativistic geodesy applications that improve understanding of Earth's gravitational field variations. These measurements support geological research, climate monitoring, and natural resource exploration by revealing subsurface density variations that affect local gravitational fields and consequently local time passage rates. The precision achieved by contemporary atomic clock technology allows scientists to test whether fundamental constants truly remain constant throughout cosmic time. Variations in the fine structure constant would indicate that the basic parameters governing electromagnetic interactions have changed since the universe began, potentially revealing new physics that connects cosmology with quantum mechanics in unexpected ways. Such discoveries would represent profound extensions of Einstein's work, showing that even his revolutionary insights captured only part of reality's deeper structure. Einstein's simple tram thought experiment launched a revolution that transformed our understanding of space and time, revealed the relativity of simultaneity, demonstrated space-time curvature, and enabled technologies like GPS that define modern life. The ACE's mission represents the latest chapter in this ongoing exploration, using precision timing measurements to probe fundamental questions about the universe that continue guiding physics research. Each new measurement reveals that Einstein's century-old insights about frozen clock hands have become far more than theoretical curiosities. Today, these theoretical insights operate invisibly within billions of devices worldwide, transforming Einstein's tram visualization into practical technology that defines modern civilization. That spring evening in 1905, when Einstein imagined frozen clock hands on a burn tram, has become the invisible foundation supporting smartphones, navigation systems, and communication networks across the globe. The patent clerk's simple thought experiment now guides every GPS calculation, synchronizes global financial networks, and enables precision measurements that probe the deepest mysteries of quantum mechanics. His visualization of time slowing down at light speed created the mathematical framework that makes modern technology possible, proving that the most profound scientific discoveries often emerge from the simplest questions